Hello everyone and welcome back. You know, everything you're doing right this second, watching this, scrolling through things on your phone, sending a message, it's all powered by literally billions of microscopic little switches. They're called transistors, and they are, without a doubt, the fundamental building blocks of our entire digital world. So let's take a closer look, shall we?
And no, that is not an exaggeration. The main processor in whatever device you're using probably has more transistors than there are people in most countries, and they're all firing away in perfect sync. It is an absolutely incredible feat of engineering that, let's be honest, we usually take for granted.
Right? It's a word we hear thrown around all the time, but if you ask most people to explain what a transistor is or how it works, they'd probably draw a blank. So today we're going to break it all down, starting with the very basics.
Okay, first up, the transistor revolution. We're going to start with a really simple definition, look at its three key parts, and then use an analogy that's going to make it all just click into place.
Now, the most important word here is control. A transistor doesn't actually create electricity, it acts more like a valve or maybe a gate for it. And because it's what we call solid state, which just means it has no moving parts to wear out, it can do this job billions of times a second with just incredible reliability.
So every single transistor has three of these terminals. Think of it kind of like a plumbing system, right? You've got the emitter, which is the source of the electrical current. Then you have the collector, which gathers up that current at the other end. And right there in the middle, you have the base. And the base, well, the base is the magic ingredient. It's the little tap that controls the whole flow.
Here is probably the best way to visualize what's happening. I want you to imagine the emitter and collector are like a huge dam, and they're holding back a massive river of electricity. The base is just a tiny little lever that controls the floodgate, so a very small push on that lever can unleash this huge, powerful current. That, right there, is the core principle.
Okay, so it's all about control. But, just like there are different types of faucets, there are different types of transistors. The two main flavors that you're going to run into are called NPN and PNP.
So the main differences really just come down to how they're built and how you activate them. An NPN transistor turns on when you give its base a positive voltage. A PNP is just the opposite. It turns on with a negative voltage. Now this difference basically decides where they get placed in a circuit, whether they control the connection to the power source, which we call high-side switching, or if they control the connection to the ground, which is known as low-side switching.
And hey, here's a fantastic little trick for telling them apart when you're looking at a circuit diagram. The little arrow on the symbol is always on the emitter. For an NPN transistor, just remember that the arrow is not pointing in. Simple, right? So that means for a PNP, the arrow has to be pointing in.
All right, so we know what they are and that they come in two main types. Now let's explore their first major job, using that gate function to act as an incredibly fast electronic switch. Let's go back to our gate analogy for a second. With no signal at all at the base, that gate is locked shut. The transistor is off. But the moment you apply just a tiny little current to the base, whoosh, the gate swings wide open, letting that main powerful current flow through. This simple on-off, 0-1 state is the fundamental language of all computers.
And this simple on-off function is just everywhere. We're talking billions of these switches firing away inside your computer's processor, allowing for these incredibly complex calculations. It's how microcontrollers in your appliances make decisions, and it's even how you can control something as simple as turning an LED on and off.
But switching, just turning things on and off, that's only half the story. The transistor has another equally powerful trick up its sleeve, amplification.
This is amplification. A transistor can take a tiny, weak input signal, like, say, a faint radio wave from a station that's miles away, and use it to shape a much more powerful current. The output becomes a perfect, high-volume copy of that original signal. It boosts the signal's strength without changing its message.
Now, if we want to get just a tiny bit technical, this is where that beta value, or what's called current gain, comes into play. Just think of beta as a multiplier. For every 1 unit of current you put into the base, you get beta times that amount of current out of the collector. So if your beta is 100, a tiny signal instantly becomes 100 times stronger, and that, my friends, is amplification.
And where do we see this in action? Oh, everywhere we need to make a signal useful. Your stereo amplifier, it's boosting a music signal to be strong enough to drive your speakers. Radios are amplifying faint signals from the air. Even super-sensitive scientific instruments use transistors to amplify tiny readings from their sensors.
So, there you have it. We've got two fundamental jobs, switching and amplifying. And when you put millions and now billions of these things together on a tiny chip, you get the modern world.
And that really is the bottom line. It doesn't matter if it's the simplest smart light bulb or the most powerful supercomputer on the planet, every single piece of modern electronics relies on these two principles. They truly are the heart of our digital age.
And that brings us right back to where we started. The device in your hand right now is living proof of this incredible technology. It's basically a symphony of billions of tiny switches and amplifiers all working together in perfect harmony just to bring you this explainer.
The transistor was such a revolutionary leap. I mean, it took us from computers that filled entire rooms to devices that we can slip into our pockets. It really makes you wonder, doesn't it? What's the next tiny giant that's going to come along and fundamentally change our world?